Okay, so this is a little bit different than the last talk, because no data. I'm just going to talk about code. Actually, I do have some Excel numbers in here, so watch for them. Okay, so I'm going to talk a little bit about some work I've been doing on a dependently typed core calculus for Haskell, for the Glasgow Haskell compiler. But before I get started, this is the most important slide of my talk. I want to acknowledge that language design is not something that you do by yourself. And so a lot of this work has been done with my fabulous collaborators. Okay, so what I want to talk to you is kind of a project I've been working on that I kind of call the Dependent Haskell Project. And my goal for this talk is to tell you two things, to talk about two parts about this project, right? On one hand, I want Haskell to grow up. In Phil's words, I wanted to become more like a dependently typed language. And I'm going to do that by extending the Haskell compiler. But at the same time, I'm paranoid about being wrong, right? I see some of the spreadsheet errors that Ben has just shown us, and we're not special, right? We make mistakes too. And so I want to do these type system extensions. I want to do my work in a way that will help me catch my errors. And so my solution to that is to make sure that I do my work with the help of a proof assistant. Okay, and so my inspiration for extending Haskell, of course, comes from these dependently typed programming languages, Coq and Idris and Agda. These are languages that have developed from the beginning to have dependent types as a fundamental part of their computation. But that's not the case for Haskell. For Haskell, we kind of have to work a little bit harder, right? So if we want to do something that looks like dependently typed program, there's a number of language features that, if you turn them on, they give you something that starts to look like dependent types, right? So I have to do this example. I guess maybe you could call it the MNIST example for dependently typed programming, right? So it's length index vectors. Right, and this is just to show you exactly, what are we trying to do? We're trying to use the type system to help us capture constraints, capture invariance about our code. And so you can write this. This is Haskell code that you can write today, right? We can define what natural numbers are, and then this definition. It's another version of natural numbers, right? You notice we have a 0, we have a successor, but the type of these natural numbers tells you they're bound, right? These numbers aren't infinite. They don't go up forever, right? They are bounded by some other natural number. So their type can tell you, I'm going to be some number in the range up to 0 to some n. And we can use these indices if we have a vector, if we have some kind of linked list that is keeping track of its length. We can use these bounded indices as part of a lookup function for that list. Right? To know that if we have some index that is within the bound of that vector, then this is going to be that we're always going to be able to look up and find the value that's stored at that position. Right? We're always going to find some console that has a value for us. And in fact, the type checker is going to know that we're never going to get to the end of the vector too early. Right? And so that's the kind of invariance. This is just a simple example, but it's an example that's often used to kind of demonstrate sort of the power that dependent types have. Maybe you don't find it so convincing, but I will say that dependent types in Haskell are something that is out there and does get used. Right? So this, I'm going to point out to so this is an experience report that just appeared in the most recent ICFP, and it is about the Galois Corporation. They use a lot of these advanced features as part of some of their projects to maintain invariance through the development of that work, right? So in particular, so I know about this project because I spent my sabbatical last year visiting this group and working with their tools to see exactly how they are using dependent types. They are using it to, it's a typed intermediate language. They want to create static simulators where they want to be able to write some verifiers for code. So they're very much concerned with correctness. And so they use the dependent type extension in Haskell to help have more confidence in their work. And I'm going to highlight two things from their abstract, right? So one thing it says, I don't know if you can see this, right? One thing they say is that the dependent types, they bring significant value. And they will be happy, but also at a high cost, right? And that's where we have more work to do, right? So what's going on? Why is there a high cost? What can we do about it? How can we make it easier for them and for anybody else who would like to use dependent types in their work? Okay, so here are some challenges, right? So they actually talk about some of these challenges in their paper, right? But I want to talk about some of them, right? And I'm going to demonstrate to you why these are challenges specific to Haskell, right? Of working with dependent types in Haskell. So the first thing is Haskell isn't a dependently typed language. Right? So that's one of the biggest challenges. And so, in fact, it lacks this pi quantifier, which is sort of the type of a dependently typed function. And so that has to be coded up using this technique called singletons. Now, so there is a library to support this in Haskell, but of course it would be better if this was more primitive in the language. The second thing that is a big challenge for Haskell is that you go to a dependent type system. One of the attractions for it is its uniformity, right? The fact that programming at the type level is the same as programming at the term level. This is not true for Haskell. And then the third thing that is specifically difficult for Haskell is that compared to Agda and Calc and Idris, it doesn't have a very strong language for doing proofs, right? So the other systems were developed originally as proof assistants, so they're very good at doing proofs. Haskell kind of lacks that. And I'm going to talk about the first two things more during this talk, and I'm just going to hint at what we can do for the third one. Okay, so let me just make it more precise, sort of what I mean by the fact that Haskell isn't a dependently typed programming language, right? So this is a function that you might want to write in a dependently typed language, and you can tell it has this pi type, right? And so what it is, it's a replicate function. So given some number, and maybe we're going to have some value, I just made it bool for simplicity, we're going to create a vector that has n copies of that value. Right, and it's not hard to write. We just write it by recursion, structural recursion on the number, where we just cons that many numbers. Okay, so we can't write this in Haskell, though, right? And why can't we write this in Haskell? We don't have this pi, right? So what do we do instead? So in Haskell, instead, we create a new data type that we are going to use instead of natural numbers that's isomorphic to natural numbers, and that's what we're going to dispatch on instead, right? So, this new data type, it's called a singleton, because, for example, if this was singleton 3, then there would only be one value inhabiting it. It would look like a 3, right? So, for example, the only thing that has singleton 0 is this singleton 0 constructor. And if we have a successor, a singleton of successor, well, that's going to be inhabited by the successor. And that's how we can kind of tie together the two aspects of what's going on with a pi type. So when you have a pi type like this n is being used in two different ways, right? It's being used as part of the type here, dependently, but it's also being used at runtime. We're doing this runtime dispatch, right? And so we kind of split those two uses with the singleton, so we can have a type variable that does the constraint, and then a completely isomorphic term argument that has to be lined up from its type, and that's what we're going to dispatch on. So it works, but it's a bit clunky. Right? And it's a barrier to entry for dependently typed programming in Haskell. What about the lack of uniformity? Right? Well, we'll program at the term language in Haskell, and here's the same functional program. We can write it in the type language to appear in a type if we like, but we have to use a completely different syntax. And maybe it has slightly different semantics when we write. Right? We're using two different structures to implement this one and that one, and we don't know whether they're going to do exactly the same thing. In fact, you notice that in the type language, we can actually write the original dependently typed function we wanted to write in the first place. The type language of Haskell is a dependently typed language. It's just that we can't do it at the term language. Right? So in the type language, we can just use these natural numbers. It can be dependent on it, and we can dispatch it on it, but only in types. Right? So we're missing that uniformity. And what's the cost of not having that uniformity? Well, it's harder to bring people, it's more complicated. It's harder to bring people on board. It's harder for them to understand how to work with these code. Okay, so as a solution to this problem, right, I'm going to talk about some work that I've done on proposing a new intermediate language for GHC that actually has dependent types in it. Right, so it's going to replace GHC's existing language, and since it's based on dependent type theory, those two problems that I showed you with singletons and this lack of uniformity, they're just going to go away. Okay, so let me just show you a picture. How do we change GHC? How do we change Haskell? Right, so this is kind of what, this is actually an old thing I took off the GHC website a long time ago, right? But this is kind of the picture of what GHC looks like, right? You take a source Haskell program, you figure out what the names are, you type check it, and then you compile away all the special forms to what's called core. And this is the important part. This is a strongly typed intermediate language. It's still very high level that, it's based on the lambda calculus, but this is what the optimizer runs on. And this, in some way, kind of is the most explicit explanation of what's going on in Haskell. Right, and then once, after a couple of core passes have done, then the code generation phase starts, and then we get code that we can run. Right, so if we're going to extend Haskell, a good place to start is by first extending core. Right? Why is that? Well, first it lets you skip the hard stuff first. Right? You do have to come back to the hard stuff, but you don't get stuck on hard stuff like namespace issues or pattern match compilation, things that aren't quite what you want to think about at that point. Right? So it's better to start where we're closer to what the semantics are. Right? And another reason to work with core is because we have actually a mathematical specification of core. So core itself, it's still pretty complicated, right? It's a language implemented inside of a compiler, but we have mathematical descriptions of that language, right? And those are called System FC, right? So this paper here from 2007, right, is the original description of here's a mathematical model of what the core intermediate language of Haskell is, right? It's based on System F, but it adds System F something that's called type equality coercions, right? These are explicit proofs of equality, and they're there to make type checking in core dirt simple, right? The core language doesn't have to do anything complicated to type check because all of the information that it needs is just right there. If we need to decide when two types are equal, we have this proof that shows that those two types are equal right there in the core language. Now the System F with type equality coercions, it's been extended a couple times to increase its expressiveness just so that we could write the examples that I showed you earlier, like vrepl. Right, but it's still fundamentally a System F-based language with extensions, right? And that's the part I want to change, right? That's the part that we're going to take out. We'll leave the coercions, the type equality coercions, but we're going to exchange the basis on System F with the basis on a dependently typed language. Okay, so don't we know how to do dependently typed languages? There's a lot of them out there. But Haskell has its own challenges, right? So first of all, we can't just break Haskell and make a lot of existing code not work, right? So whatever solutions that we propose, there's just not going to be a starter if the first thing that happens is suddenly the core libraries don't work anymore. You make small changes and people grumble, but you can't make very large changes. Right, so we have this existing compiler we have to preserve. The other really big thing about Haskell is that it doesn't have a termination checker, right? the consistency proof for these logics of Coq and Agda is based on the fact that all programs terminate. This is not true in Haskell. Yeah. Yes, yes, exactly. Yeah, so that's going back up to the first part, right? It's an existing compiler. It's a big existing compiler with lots of extensions. So whatever we have has to be compatible with all of those extensions. Exactly. All right. Yeah.
But the Haskell community has not been really careful with that, right? With FTP.
Yeah, I know.
All the old languages all are now obsolete. So.
Yeah, we added. Yeah. I mean, the libraries committee changed one type class, or well, not FTP, but like applicative, right? You know, just all that pain just for one very small change, right? Okay, maybe I should just change it all, but I don't know. I don't know what's going to happen, right? Maybe I should just call it all. What did you say? Multivariate functions. Okay, what else is different about Haskell, right? So we have to deal with the fact that things don't terminate, right? And how are we going to do that? And that's going to influence the proofs that we do, right? Because they have to be robust to the fact that termination is allowed at any point, right? That kind of relates to the next point, which is this coercion language. In FC, it's system F with these equality coercions. Because this language may not terminate, right? We can't do what Coq and Agda do, is define equality based on reducing types to normal forms, because we don't necessarily get normal forms. So instead, we could just require that, you know, if they happen to reduce to a common form, we can provide some evidence of what that reduction looks like, and we can check that evidence. And so at the core level, we're guaranteed to have decidable type checking, even if maybe some source Haskell programmers are willing to turn off termination checking for types. And then the last thing that's really important for Haskell is that we expect when we run Haskell code, we're not having types and coercions around, right? This checkable evidence, it's just there to keep the type checker happy. Right? We don't have a performance cost for it. And maybe I feel strange talking about performance costs in Haskell, but this can be significant, right? If every polymorphic function has to take this explicit argument, that can really add to the running time of Haskell code. Okay, so what does the world look like today? Right? So this is my slide with Greek on it, right? But this is sort of the syntax of what FC with these type equality coercions and a whole bunch of other extensions looks like. So we have here's in the term language, right? We have what's here, what's in this language, right? So we have some constants, like, you know, true, false, 3, right? Maybe we have some functions. It's a lambda calculus. We have polymorphism, so I'm just writing, we're abstracting over a type variable and applying to a type variable. And it's explicitly typed language, so in the core language, we have to say exactly what type we're instantiating everything in. This is where the equality coercions come in. If we have A and we want to change its type from some type A, capital A, to some equivalent type B, then we have to have gamma. This little gamma is going to be a proof that these two types are equal to each other. So anywhere we want to change one type out for an equivalent one, we have to mark that in our source code. And then again, that makes type checking very trivial in this language, which is good for the compiler. Since we have these coercions, we can make them first class. So the language also includes the ability to abstract a proof that maybe A is equal to B, and maybe supply it to some context. Okay, so that's the term language. Here's where the duplication comes in. We have, if you go look at the type language, we have all the same things again. Slightly different forms, right? But we have constants there. We have functions there. We don't have lambdas, but we do have the ability to apply things to arguments. Those functions can be dependent in the type language if you use the type and type extension, like I showed you with VREPL. We have equality coercions in the type language, again, to support the type and type, and we can abstract over them in the type language. We still don't have lambdas, but we can have data types that generalize over them. So we have a lot of the same things going on in the two different languages. And so why don't we just glue them together, right? Let's combine them, right? And so here's what DC looks like, just a syntax, right? It just takes all the types and terms and kinds and puts them all together in the same language so that we can reuse the same structures for both, right? So we could still we only have one, constants only appear in one place in our syntax, but we can use them anywhere, right? And we have dependent functions as sort of the primitive form. And then here's something really important, right? So I said that we had to be able to erase types, right? But we don't know what types are once we combine things together. So we have to have two different kinds of dependent functions, regular dependent functions, and ones that I call irrelevant abstractions. These are dependent functions that promise not to use their arguments so that we can erase them, right? And so instead of making a syntactic distinction, the only thing you can erase are types and you can't erase anything else, we're making our distinction based on what we actually care about, whether we're going to erase it or not. Right, so we put in two different kinds of dependent functions, and then we could still also have equality coercions and coercion abstraction, just like we had before. Okay, so this kind of simplifies the syntax, and once we have the simplified syntax, so what does that mean, right? So that fixes two of those problems I was talking about, right? Like the lack of uniformity, right? You could see how things could get out of sync if you have one mechanism in syntax for one thing and another mechanism in syntax for another thing. If I share them, they're going to be more likely to keep the same semantics. And then singletons, well, this is introducing a pi type into the term language. So that means we're not going to have to fake up our pi types, but at the same time, we're still going to have that erasure ability by having these irrelevant arguments. Okay, what's the drawback? Things get a little hairy, right? So our typing rules for this language, they're big, right? And I show them to some of my co-authors who are more on the implementation side. They're not so eager. So what do I do about this, right? So So we have this complicated type system now, right? How do we know it's right, right? I want Haskell to have a type soundness language, have type soundness. I want it to be type sound. How do I know that after I've changed everything, I took those two different syntaxes, mushed them together, how do I know it's still type sound? How do I know I can still, I assert that irrelevant abstractions can erase their arguments. How do I know for sure that they can? How do I know that coercions can be erased? How do I know that I can type check, right? And then at the same time, when we developed this language, there were a lot of questions. Some things weren't obvious. How do we know that we got it right? Could we have made a different choice and still had it work out? And what does it mean? So if I'm explaining this language to other people, how do I explain what the computation is? It's not a very good vehicle for explaining Haskell, and that's really what I want it to be, right? And so one part of the solution is to double our workload, right? So if you think about the language I showed you, DC, it had a lot of annotations in it, right? Lambdas were annotated with their types, but we also had irrelevant argument. Whenever we had a polymorphic function, we had to say what it was applied to, and we had these coercions everywhere, right? And a lot of the semantics of the language, when we define those big, hairy rules, some of it was for explaining how computation works, but some of those rules were talking about how do we push those annotations around, right? And how do we know which is which? So what we've done is we have created another language that we just call D, because we're losing the explicit coercions that we had just developed in DC. And these two languages, they're supposed to be the same. And what do I mean by the same? Right? So if you have a term in DC, it has a lot of typing annotations and coercion annotations on it. We could just drop them all. That's going to give us a valid D term. And then we also should be the case that if we have something that, this is a typed language, it's just as implicit. There should be a way to take any term that's well typed in D and add enough annotations so that we get a valid DC, right? But what we get from the end, right? We get this much cleaner D language that loses anything related to pushing annotations around. Sorry. Right, so we have these two parallel languages, right? And the important thing is, in DC over here, we have a bunch of these explicit coercion proofs that say when two types or two terms are equal to each other. In D, those things turn into something that looks a little more familiar to dependently typed languages, right? It just looks like a definition of when things are equal. And in this language, we can just use it automatically. And if we can use it automatically, then we know it's not relevant for computation. If it can be implicit and we have the same semantics between these two, then we know we can erase it. We don't have to have it around at runtime. And the nice thing about it, having these two languages that are connected to each other, is that we can do our meta theory in the version of the language that makes the most sense. Right? It's a lot easier to prove progress in this implicit language. Right? But it's a lot easier to prove preservation in the explicit language. But then we have these annotation and erasure lemmas that connect the two together that will transfer the proof from one language to the other. So the second question. You should still be worried about this complexity, right? Did we get it right? Right? Because part of the solution made it easier to explain, but it added a lot of extra math that we did. Right? How do you know we didn't mess up when we were doing that mathematics? And so the second solution is to do that math in a proof assistant. Right? And so what we did is we proved all of these results using Coq so that we could have Coq both help us check the result, but also help us generate them. Right? Since we're working with these two languages, the two languages are quite big, right? So just specifying the two languages took about 1,400 lines of Coq, and then about 17,000 lines to do these proofs, right? And I'm not sure we could have approached languages of this scale with this team without having this kind of tool support. And I will say that we relied on two additional packages to work with Coq to help make our system a little bit easier to use. So one tool that we used, the OT tool by Peter Sewell and his group, it is a way of specifying languages in a way that you can generate both the definitions in Galena of the semantics of your program, but also the LaTeX macros that you use when you write your paper about that language. What does this mean? It means that you don't have typos in your paper, because your paper, when it has a rule that comes from here, you've proven that that rule is the right rule, right? So just like Phil was talking about, make sure it's really great to work with literate code. This is another way to make your code literate, maybe a little bit more roundabout. The other thing that we did is we had another tool that helped us with some of the variable binding that generated a bunch of lemmas for us and proved them, so we didn't have to worry about that. Here's my data. Right, just so that you can kind of see how, the OT, it doesn't really compress the specification, like 1,400 lines OT, and then it comes out with just a few more lines in the Coq specification. There's no comments, no blank lines. Yeah. doing, the changes you're doing, are compatible with whatever else is in GHC. And so I want to talk very briefly about two different extensions that we built off of this code base, right? So that we didn't have to, like, when we went to the next paper, we didn't have to start from scratch. We could extend our proofs with new rules. So the first one, so this is a little bit about making Haskell's proof language a little bit more expressive. So the version that I talked about with DNDC, it gave you beta equivalents for functions, but it didn't give you eta equivalents. And so we wanted to see whether we could add eta equivalents to our proof language so that we could prove more functions equivalent to each other, right? And eta equivalents, it's not a very big extension, right? So we have three different kinds of functions. So it's 3 new rules in D, 3 new rules in DC, so 6 new rules. And so we put it in our specification, and Coq is really great about pointing out, here's where you need to fill in the cases that for these new rules. And so I asked an undergraduate to help me on this to finish these proofs after this extension. Now, it wasn't all rosy, right? So one of the rules did force us to rethink one of our major lemmas, right? If you know when you're working with Coq, it's really great if you can do induction on structure. That new rule made us change it to induction on height. It wasn't so bad because Ellingen gave part of that 11,000 lemmas. Some of them were about height, so we had that available to us. So it wasn't so bad to change that existing proof to be an induction on height. Another thing that happened was that one of our properties that we had proven before was false, right? And this was kind of a surprise to me because we were trying to prove it, we couldn't prove it. And then, of course, we tried to figure out why we couldn't prove it. We found a counterexample, right? But it turned out we didn't need that property anyway, right? It wasn't important for our proof. And I wouldn't have been confident about that we didn't really need the version that we need unless Coq told me so, right? I had taken something and I had weakened it, but that was still fine. I could just rerun my proof scripts and know that I haven't lost the real properties that I cared about, right? And because it really kind of bothered me that this property failed. But we still type sound, even in that situation. Okay, the other extension, right, is a much more significant extension where it combines, so Haskell has this feature called safe coercions. It allows you, if you have a new type, to be able to, for free, coerce between the new type and its underlying representation. You don't have to pay any cost to do that coercion. So it allows you to have these abstractions without any cost. And in order to make sure that those coercions are safe in the context of Haskell with so many different interacting features, Haskell has this feature called roles that track where the coercions are available. And it fundamentally boils down to having 2 different notions of equality, right? So the normal Haskell equality, that's kind of called nominal equality in the roles world. But if we can do, there's a coarser equality that for the things that are allowed to be coerced together, that's representational equality. These 2 things, they may not have equal types in Haskell, but they have coercible types, so we can easily and cheaply coerce between them. So doing this right took a pretty significant extension, right? So suddenly our rules went up from maybe 34 rules to the system to over 100 rules. And part of the reason was we really wanted to make sure that when we did this extension, we could the need for being very careful with roles comes about from type families, which is the ability of Haskell's type level to actually dispatch on types. And so we had to make sure that we had that ability in our language to be confident that our proofs were meaningful, that we weren't subject to some type soundness flaws that this kind of coercion had in Haskell in the past, right? And so why did we need so many rules just to model this this sort of type dispatch that type families do? Now the advantage of it is since we're doing it in a dependently typed language, instead of in Haskell as it is today, this is actually a justification for us to put type analysis even at runtime, if we wish. We'll at least have preservation of progress for that kind of extension. Right, so it kind of opens it up, because of that uniformity, it opens it up to more extensions in the future. Okay, so I think I'm going to stop there. I don't want you to think that you can use dependent Haskell tomorrow. This was solving the problems at the core language level, right? But there's still a lot of source language issues, and the source language issues really have to be worked out in the context of the Haskell community. So GHC has a proposal process, which involves a lot more people discussing it, slows things down, but it also kind of brings in more people into the language design process. So it's overall a good thing. I also would like the proof theory of the core language and of everywhere in Haskell to be more explicit. I think this is a great place for more theoretical research into Haskell's type system. But I do want to say that, we're real good at doing proofs about small languages, and we're real good about doing formal verification of C compilers. But we need stuff in the middle, right? We need to be able to reason about just slightly bigger languages that are a little bit more complicated. And so I think it's really important to bring in the proof assistance, not just for artifacts that we use, like COPSERT, but also for our mathematics as well, right? So I'm kind of very happy that Phil brought up the Poppelmart challenge in his talk, because I believe it just as much today as 14 years ago when we put it out, that proof assistants are there to help us out. Now, I would like if, so maybe the AI folks here, helped us have developer tools for proof assistance catch up to the developer tools for Excel and other frameworks. I feel like I'm programming in 1999 whenever I use Coq. I would love to have that catch up. Right. So I hope you understand that. I kind of feel like we know where to go with having a core language. It's still going to take a little while to implement it in the full compiler. Okay, thanks.
Stephanie, thanks a lot for a great talk. So have you looked at Lean as an alternative to Coq?
I haven't looked at it much.
Okay.
I am excited about it. It does seem to be rather a moving target, so.
Yeah, but it just keeps getting better. So,
yeah.
A quick question. So, in the beginning, you said that DC is an extension of FC. Mm-hmm. Is that a superset, strict superset, or not really? Or?
So we didn't prove this because I didn't want to triple my work and put a model of FC in Coq as well as D and DC. But I believe that anything in FC you can translate into DC.
So when you're fixing the compiler, so when you compile from Haskell to DC now, now that's a different translation, right?
Yeah, it's a different translation, but I think it should not be hard to keep the status quo. Right. The nice thing about working in the core language, you make all the changes you like as long as nobody notices. Right. And then once you have the core language in place, you can slowly reveal them as brand new shiny features.
Okay, thanks.
The last question.
So for some of these next stages where you're going to be doing changes around, about namespaces and all these other surface level features, is that going to be something that we can still enjoy papers of yours at ICFP? Or is it, or not? I mean, how are you going to navigate that with, the interaction with the community? Or are there just going to be like huge author lists or something?
That I don't know. I mean, how do we evaluate whether we have a good solution for that, right? ICP is really good about saying, yes, your proof is true, except this is an important proof, but hey, you did a lot of work to come up with a very nice language design that fits into this setting where it's backwards compatible, so it's got a couple of warts, but overall it looks nicely. That's a much harder paper to write. And we need to come up with good ways of writing those papers and also encouraging people to write those papers.
All right, we have to cut off here. Let's thank Stephanie again.